Okay, we need some practice on setting up these logarithmic equations. Some of these can be solved by using your calculator, and some of them you do not need your calculator. So keep an eye on the non-calculator icons, because the non-calculator could appear in your first part of your exam, and the ones where you use your calculator would be in the second part of your exam. So the basic thing here is that we have to apply the rules that we've learned for log properties. For example, the product property, the quotient property, and the power property. So as I go through, I will encourage you to apply the properties that you've learned in order to simplify the problem. So in number 26, I have the natural log of this quantity. X plus 4 is 2. Now I want to get to the answer. So the best way to accomplish this is to re-express this problem exponentially. So you know that the natural log means base e. This is your exponent. This is your answer. Once I've set this up, this is simply an algebraic problem where I have e squared minus 4 equals x. Enter that in your calculator, let the calculator do the computation, and you will end up with an x value that's decimal, and you will round off 3 places. So put that in your calculator and check it out. Number 27 is also a calculator problem, and it's not much different than number 26. The difference is, however, that this is a base of 7. We're still looking for x, which is part of the answer. We'll still use the same approach. Rewrite exponentially. Base, exponent 2, answer 3x minus 1. This is simply an algebra problem, so I have 49 equals 3x minus 1. I'm going to bring 3x over here and say this is equal to 50. And I put that in the calculator and I get x equals 16 2/3. Not a difficult problem. Number 28, 29, and 30. Notice that the icons indicate that this would be a non-calculator problem. Okay, I have a little issue here. I must have cut off. This is equal to 1. Sorry about that. Okay. So when I have a problem when there are 2 log terms and they're on the same side of the equation, then I can simply apply the property that says if I've added 2 logs with the same base, then I can re-express them as 1 log, same base, but the product of the answers. Now I've gotten it down to a manageable one log term equation, and I'm going to use the same approach I did in 26 and 27. You use the base, the exponent, and the answer. Alright, this again becomes an algebraic problem where I have 5 equals x squared minus 4x. It is quadratic, so I will set it equal to 0 by bringing the 5 over. And I can solve it by factoring. And I would get a negative 5 and a positive 1. Then I have, for my final solution, x equals negative 1 and x equals 5. Now you need to caution, you need to stop here and think about what your answers are trying to do. You're trying to let them represent the x in the original equation, remembering that the answers in a logarithmic term cannot be negative. If I were to substitute negative 1 into the first term of the equation, the answer here would be negative. That is not allowed. So you need to take and cross off negative 1. Now let's check 5. 5, if I place 5 in place of x, that will work. And if I place 5 in the second log term 5 minus 4 is positive, that's okay. So I do have a solution of x is 5 only and negative 1 is extraneous. 29. Oh, this one has a lot going on. It has two terms on the left side of the equation and one term on the right. So in between the two terms on the left is a negative sign, and that comes from the quotient property. Because they have like bases and there's a subtraction sign between them, I can re-express or condense this into one term. The first answer is the numerator of the quotient, and the second answer is the denominator of the quotient. I'm going to do one thing on the right side. I'm going to pull that coefficient of 2 up as a power of 2. So that would be log base 2 of 2 squared. Now we're getting to a point where I can say, if you have one log term on the left and one log term on the right, you can simply drop the log terms. So I will take and equate the two answers. Now I'm going to write this as a 4 now. And I have a fraction on the left and a number 4 on the right. I'm going to clear the denominator by multiplying x minus 1 times each side mentally, and I would get 4 times x minus 1. Now we have a linear equation, which is easy to solve. I have x plus 5 equals 4x minus 4. I'm going to pull the x to the right, get 3x, and the negative 4 to the left and get a positive 9. And I have x is equal to 3. Now, not so fast. Let's go back and check it in the original problem. If I input 3 in the answer of the first log term, 3 plus 5 is positive 8. That's okay. If I input 3 in the second log term, I have 3 minus 1 is positive 2. That's okay. So I'm safe to say that that is my solution. The last one has a relatively simple problem, but I have one log term on the left, one on the right. Now I wish the 2 weren't there, but it is, so I have to deal with it. What I'm going to do is I'm going to try to isolate the 2 on the left by pulling the negative log x to the right, and that is I would have to add that to both sides. So I have the log of x plus the log of 20 now. Okay. Why is that good? Well, that's good news because I have the sum of two logs with like bases, and I can condense into one log term, and that would be the quotient property. So I have the common log of 20 times x. Now that I have it down to one simple log term on the right, I will handle this like I did numbers 26 and 27. I will simply re-express this as an exponential equation. Common log means base 10. 2 is the power. The answer is 20x. The left side is 100, 20x. And of course, 20 times 5 is 100. Not so fast. We need to check the replacement or substitution. If we put 5 in the original equation, the log of x is 5, is positive. We're good. So that is your final answer, and you have solved 5 log equations.